Alright, so in the previous lecture what we saw was that every vector space V of dimension n over f is isomorphic to Fn. Alright. So for example, what we are trying to say here is that if I have vector space V over R, then this looks like, and its dimension is n, then it looks like Rn itself. Fine. Now we are saying it looks like Rn, but in Rn we have something nice. We have what is called a standard basis. Fine. So we have a standard basis E1, E2, En. Fine. Can we have, so the question arises, can we have a standard basis as well? Fine. That's one thing. There could be choices in the sense that if I am looking at V, I can look at V differently, somebody else can look at V differently, and therefore we may get different bases here. Fine. So we have to understand what do I mean by a standard basis, that's the one thing. So depending on the question, things are going to be different. Fine. And how do I do this to get the standard basis? So there is a notion of what is called an ordered basis. So let us take an example to make you understand what do I mean by ordered basis. So let me take V as, so I have written it as U, V, W, X, Y belonging to R5 such that minus V plus W minus X is 0, V minus Y is 0, and V plus U plus V plus X minus this is equal to. So I have looked at this as my V, and this is a subset of R5, you already know, nothing special. So it is nothing but the null space of, so V is nothing but the null space of A, where A is nothing but, look at the component coming from V is minus 1, 1, 1, oh there is U also, so let me write first U here. So U is this, there is a U here, V is minus 1, 1, 1, U, V, W, W is 1, 0, 0, then you have X, X is minus 1, 0, 1, and Y is 0, minus 1, minus 3. Fine. So what you are supposed to do is look at the RREF of this. So RREF of this you can write it as 1, 1, 0, 1, minus 3. Fine. Then you have already 0, 1, 0, 0, minus 1, 0, minus 1, 1, minus 1, 0. And from here you will get it as 1, 1, 0, 1, minus 3, 0, 1, 0, 0, minus 1, 0, 0. Just add it, these two, the last two. You get 1 here, minus 1 here, minus 1 here. And you can use this to make this one 0. So this is your pivots. This minus this will give you 0 here. Then this minus this will remain this, and this will give you minus 3 plus 1 is minus 2. So accordingly rewrite the things. So you can see that in this example the solution is this. So the solution is U, V, W, X, Y. So which is same as, look at this part, here it says minus X plus 2Y, this part says it is Y, this part says it is X plus Y, then you have X and Y here. So it gives you minus 1, 0, 1, 1, 0 and 2, 1, 1, 0, 1. Alright, so this is the basis that I get. Fine, so you can compute it yourself. So what I would like you to understand here is that any element here is a linear combination of this. So any element of V is a linear combination of elements from S. Fine. So, as we started in the system of equation, we said that my first column corresponds to the variable x1, second to the variable x2, and so on. So, if I can say that at the back of my mind, at somewhere I keep a track that this is my first vector, this is my second vector, then I can say that I have already fixed my vectors u1 and u2, and since I have fixed it, I can understand it in a different way. Fine. So, what I am trying to say here is, so let me just proceed further. So, I cannot take up those examples because those examples are wrong. So, take any vector there, all right. So, whatever vector you want to take, so let u belonging to V. Since u belongs to V, so I know that u will be equal to, so this will imply that u is equal to alpha times minus 1 0 1 1 0 plus beta times 2 1 1 0 1. This is what I know. Fine. So, I can write this as minus 1 0 1 1 0 as the first vector, 2 1 1 0 1 as the second vector, and then multiply it by alpha beta. I can write like this. So, which is same thing as looking at, in some sense, since I am looking at here subset of R5, so I can write like this. Fine. So, therefore, so what I am trying to from here is say that, so what we are trying to say here is that if I have fixed my vectors u1 and u2 and with u1 as my first vector and u2 as my second vector, all right. So, I have fixed here, that is important, fixed. See, the important thing is that when I write S, all right, when I write S, then it is a set. Once it is a set, so any element can appear at any place. There is no guarantee that u1 has to be the first element, or this has to be the first element and this has to be the second element. That I cannot guarantee because it is a set. Fine. So, in place of writing like this, what we do is we write B and put it as u1, a small bracket u2, or in many books they will write it as u1 u2. Fine. So, depending on which book you are looking at, they will have different ways of writing it. So, somewhere they will use the small bracket, somewhere they will use this middle bracket and so on, but we write it like this to say that there is what is called the first element and what is called the second element and so on. Is that okay? So, when I look at it as a set, any element can appear anywhere, but when I am writing it in a small bracket or middle bracket, then I am saying that what is my first element, what is my second element and so on. So, when I write like this, it means that the first column is the first element and the second column the second element of the basis. Fine. So, once I fix this idea that what is my first, what is my second, I can just think of V, any element of V as just alpha beta. Fine. And with this idea I can say that the vector E1 which corresponds to 1 0 is basically U1 for me, and E2 which corresponds to 0 1 is the vector U2 with me. Is that okay? And therefore, I am writing everything in terms of these vectors U1 and U2 or the standard E1 and E2. The notation has changed. U1 was having 5 components, E1 is supposed to have only 2 components because dimension of V is 2. So, dimension of V is 2 in this example. Therefore, I have just 2 vectors E1 and E2, each of them has only 2 components, and therefore, what we are saying is that V actually looks like R2 itself, all right. And this is what we learnt when we said that dimension of V is n. Alright, this is what we said in the beginning here itself, that when the dimension is n, then I have got Rn, it is isomorphic to Rn. So we are saying here in a different language that V is isomorphic to R2 with R2 here is E1, E2. So E1 here is U1, which corresponds to E1 for me, and U2 corresponds to E2 with me. Is that okay? And every element I am able to write with respect to that. Fine. So I would like you to understand this, that there is a way of saying that what is my first element, what is my second element. If I change the order, all right. So if I change the order, for example, so if I change the order, things will change here accordingly. Fine. So this is what you have to be careful about. You first fix your basis, that this is my first element, this is my second element, and so on, and then do your work. So this way there are two things that happens. You can easily see that V is indeed isomorphic to Rn in the sense that I have got E1, E2, En coming into play. Fine. Another advantage that I have is that when I am looking at a problem, the vectors, the size of the vectors could be very high, but the actual calculation may require only few vectors as such. All right. So if I have to look at only few vectors, fine. So I would just have to look at the linear span of those few vectors. Hence the size of the place where the problem that I am going to look at may have only a small size. And if the size is small, I can reduce my work and look at a small number of vectors and do work, and everything will be, dimension will be fine. So let me write the definition here, what I am trying to say that. So in general, let V over F be a vector space with basis S is equal to U1, U2, Un. So the dimension is n, dimension of V is n, fine. So there is a notion of what is called B, which is called the ordered basis. So I can take my ordered basis as U1, U2, Un. As I said, in some books they take this notation. I will be using this notation, U1, U2, Un. So this for the basis, and this for the basis matrix. Fine. And I will write it as a small, as this B. So there is a what is called calligraphic B here, and this is just a capital B. Fine. So calligraphic B means ordered basis, as I have already written here. It will be in a small brackets, and corresponding matrix will be in terms of middle bracket, and I would like to differentiate between the two to have a better clarity. Fine. So here I have put my U1 as the first, U2 as my second. I can also take C and another ordered basis, again calligraphic here, ordered basis as say U2, U3, U1 and so on. So U4, so on till Un. I can write like this. Accordingly, my C matrix will be U2, U3, U1, U4 and Un. Fine. So these two are different bases. This is what you have to be careful about, because I am looking in terms of ordered basis, not a basis, as an ordered basis, and ordered basis they are different. And there is a notion of what is called, so if U is any element of V, and if U is equal to alpha 1 U1 plus alpha 2 U2 plus alpha n Un, then this corresponds to, I don't know why I am writing so many mistakes here. So this is, as I said, if you recall, this is the way we write here, this times alpha 1, alpha 2, alpha n. We wrote the vectors like this, and these were the scalars that we are looking at, a scalar vector. Fine. So if you look at here, this is nothing but B itself. So what we do is that we write U, and then we put this bracket, and then put this calligraphic B to say that this is nothing but alpha 1, alpha 2, alpha n. all right, and we call it the coordinate vector of u with respect to the ordered basis B. Is that okay? So, this is what you have to be careful about. Since at the back of my mind I already have fixed this ordered basis, I do not have to write that again and again. I can just look at u, write it with respect to B and say that it is nothing but an element of Rn now. Earlier I did not know what my V was, from where V came, that is immaterial to me. What is important is that what is an ordered basis. Once I have an ordered basis, then I have an element of Rn associated with it. That is more important. Is that okay? Similarly, if I want to look at u with respect to C, all right, C is an ordered basis. So, if I want to look with respect to C, what I am supposed to do is, C had u2, u3 and u1 with me, u2, u3, u1. So, what is the component of u2? In this expression, the component of u2 is alpha 2. So, alpha 2 will come first. Then it is u3. So, what is the component of u3? It is alpha 3. Then alpha 1, alpha 4 and so on till alpha n. Fine. So, again it is still an element of Rn, but the ordering has changed. The ordering has changed as per the ordering in C. Fine. So, whatever order you are fixing, based on that everything changes. That is what you have to be careful about. So, in some sense what we are saying is that take a basis S, u1, u2, un, then an ordered basis B of V, all right, is S with an ordering, is that okay? So, there is a function f from the set 1 to n to the set u1, u2, un, and then I am saying that f of 1 is, suppose I am writing it as u3, f of 2 as u2 here, u3 here, f of 3 as u1 and f of I is equal to ui for I greater than or equal to 4, then this part, this idea gives me the ordered basis C. Fine. So, there is a basis and there is an order, both are related here in case of ordered basis. Is that okay? So, this is what you need to understand, that there is a small difference between the two and you have to be careful about. We will see the use of this at a lot of places from now on, maybe till the end of the lecture. We will see that ordered basis keeps on playing roles again and again. In some time during inner product we may not understand much, but afterwards again we will come back and we will see that it has implications, all right. So, let me write the definitions again, whatever we wrote. So, starting with an ordered basis B, which was say some u1, u2, un, I have the matrix B which is u1, u2, un, then any u belonging to V is of the type u1, u2, un times some alpha 1, alpha 2, alpha n. This is an element of Rn. This was coming from V cross, so this is coming from V as such, so let me not write V cross V cross V. So, this comes from V, fine, and you write u of B as alpha 1, alpha 2, alpha n, fine. This is the way we write. So, again remind yourself that from the very beginning of the class we have been saying that our vectors are column vectors. So, this is what I am saying, that my u, even if the u could look like anything else, but it is a vector, it is a column vector, all right. it is a column vector. And therefore, this is the idea that we have been following from the very beginning, that we want every vectors to be written in terms of columns. Fine. So, for example, just look at the previous example. The basis was wrong, so I don't know, but if you want to write, say, previous example, so previous example, let us pick a vector which will give me this plus this. So no, so let me write it is 2 1 1. All right. So if I have got this vector, so there I had u1 as -1 0 1 1 0, 2 1 1 0 1 times, if I want to do 2 and 1 here, fine, this vector is going to look like -2 plus 1 0 plus 1 2 plus 1 2 plus 0 0 plus 1. I hope I am correct. See, I do lot of mistakes, so be careful when you do copy my things. All right. So what we are saying is, if I am writing this as u, then u with respect to b looks like 2 1, whereas if I take c as this vector 2 1 1 0 1 and -1 0 1 1 0, if I take c as this vector, all right, this will imply that u with respect to c is 1 2. All right. So in some sense, x has become y axis and y axis has become x axis. All right. So you have to be careful about doing things. All right. So remark, let B be an ordered basis of V over F of dimension n. Then these things are important. A, if I take any, so look at any linear combination of u and v, this with respect to b will be equal to, so alpha is a scalar and u and v are elements of v itself, that will be alpha times u with respect to b plus v with respect to b. All right. To b, let S is equal to W1 W2 Wm be a subset of V, then S is linearly independent. All right. So let's recall things. When is S linearly independent? S is linearly independent if I am supposed to solve a system alpha 1 W1 plus alpha 2 W2 plus alpha m Wm is equal to 0. I need to solve this system and my solution should be only the trivial solution. Fine. This is what I need. So let's recall one of the results that we had, that if I multiply this by a linear transformation, if I multiply by A, fine, then what we know is that if A is invertible, then AW1 to AWM, all right, S linearly independent will imply that AW1, AW2, AWM, this is also linearly independent whenever A is invertible. This is what we had seen. All right. But here if I look at in the previous example, this vector that I had -1 0 1 1 0 2 1 1 0 1, this is not a square matrix. Not a square matrix. Fine, this is not a square matrix. So cannot talk of talk of invertibility. So I cannot talk of invertibility, but still, all right, this behaves as invertible, all right. So this behaves as an invertible matrix, because if I want to solve this, x, y here 0, all right, then this has only the trivial solution. Fine. So again, even though this matrix is not invertible, but it has only 2 columns, and the 2 columns basically form a pivot, or the rank of this matrix is 2, and hence it behaves as an invertible matrix, because this result, that when I want to look at alpha 1, w1 to so on, this system alpha 1 to this system has only the trivial solution, and therefore these are linearly independent. So in some sense, linear independence and invertibility, they are playing a similar role. So what we are saying is, then S is linearly independent will imply that this is linearly independent. Fine. Now if this is linearly independent, what does it mean? I am thinking of A as the basis vector. So if I think of A as my basis vector, say u1, u2, so here I wrote it as B, I think. So u1, u2 till un basis matrix. Fine. Then I can multiply this w1, w2, wm with a basis vector, things like that, and I will get something now. So from here I can go to w1 with respect to B, w2 with respect to B, till wm with respect to B. This is a matrix, all right. What will be the size of this matrix? There are m columns here and there are n vectors here, so each B has n columns here. So any vector will look like some beta 1 till beta n, it will look like this. So this is an n cross m matrix, and we are saying that this is invertible with a question mark, because it is not a square matrix. But what we are saying is that invertible in the sense that the columns of this matrix, are linearly independent. Is that okay? So this is what you have to be careful about. In particular, if I look at the third part that I would like to say here is that if I start with, in place of V, if I start with Rn itself, all right, and I have a matrix, I have B as a basis, corresponding to B I have this matrix u1 to un, everything here is now in Rn, all right. So this is an n cross n matrix. So since it is coming from a basis, so it is invertible, B is invertible. Thus it will imply that, thus V, if I want to write any V belonging to Rn, I want to write V as, so I want to write V with respect to B, and if I am writing this as alpha 1, alpha 2, alpha n, then can I say, will that imply that alpha 1 to alpha n is equal to B inverse V? That is the question that I am asking. All right, will that be equal? So understand it. So what I need is that I need to find, find scalars alpha i's such that V is equal to alpha 1 u1 plus alpha n un. Fine. This is same as we wrote earlier, u1 to un times alpha 1 to alpha n, and which is same as B times alpha 1 to alpha n, which you can see that this will imply that alpha 1 to alpha n is nothing but this B will come here as B inverse, and I will get this is equal to this. So this thing here, when I am looking at Rn, I get an n cross n matrix, invertibility comes, then any element is nothing but B inverse times V. Is that okay? So in general I cannot do that because I do not know the size of the matrix vector basis matrix, as it happens in the previous case. I could not talk of inverse of this matrix, doesn't make sense, fine, but still I could solve it. All right, so here when everything is nice, I get an n cross n matrix. From a small b, from this capital B, I can go to B inverse. In general, I cannot go. So you have to be careful when you can go and when you cannot go. All right, so we'll take up this idea again in the next class. Thank you for now.